Allora, probabilmente posso, probably I could start sharing my screen.
Yes. Yes, I'll stop my.
Does it work?
Yes, very good.
Okay, so it's 9:30, so I think it's time to start the session. So welcome to this HE6 session of the 16th Marcel Grossman meeting. As you know, there are a lot of parallel sessions, and this is one of them. This is fully dedicated to recent observations of cosmic rays, namely electrons, positons, protons, antiprotons, and nuclei, starting at energies, I will say, a few GeV up to the highest energy, so more than 10 orders of magnitude more. We will go through all the energy spectrum, starting from low energies and going to the highest. We will have 7 talks covering, moreover, all the active experiments, at least the ones that are producing results nowadays, but there will be also a couple of talks dedicated to future projects, both for direct and indirect, even if in space experiments. So I think that there's no reason to wait. The agenda is tight, so we'll invite all the speakers to stay in their 20-minute slots. And I leave the floor to the co-chair, Fabio Gargano, who will handle the session with the speakers.
Thank you, Ivan. And first of all, I would like to thank all the speakers for joining us today. So let's start with the first talk from Professor Paolo Zuccon on the recent results of AMS-02. Paolo is a professor at Trento University and member of ANFN. He's also national team leader of AMS-02 experiment and is interested in, of course, astroparticle physics, cosmic rays, and also experimental techniques and data acquisitions. So please, Paolo.
Hello, everyone. Thank you for the invitation. You see that my talk is titled 10 years of AMS, because just a few weeks ago, we celebrated 10 years of EMS. I will concentrate my talk most on nuclei, given the time constraint, but I'm here to answer questions about anything about EMS. As you see, AMS collected in 10 years over 170 billion of charged cosmic rays with energy up to multi-TeV. And I will give you just a review about that. Just a little reminder, this is how AMS look like. It's roughly 7 tons and consumes 2.5 kilowatts. And it operates in spaces in 2011. This is a sketch, but what I'm interested to remind you is how it works. There's a magnet, permanent one, that produces a magnetic field in this direction. So these goldish layers, which is a silicon tracker, can reconstruct a track going through the detector and bending. A system of scintillators act as trigger and time of flight, measuring beta. Then we have a transition detector to identify fast electrons from slow protons, and an electromagnetic calorimeter to measure energy of the electromagnetic component and improve electron-proton separation. And we have a ring imaging Cherenkov capable to do better than 1 per mil on beta and allow for isotopic separation. This is just a picture, sorry, it's 10 years ago exactly, launched AMS with one of the last shuttles. And what I want to give you first is the kind of accuracy this instrument is capable of. You see here sometimes, or actually often, nuclei interact into the detected material and produce a few tracks, and we trace back and find the vertex. And so we can produce a database of the three-dimensional position of these vertexes. And this is shown here. And you can appreciate that we can resolve even the tiny structures of our detector, even the writing AMS on top of the multi-layer insulation. So this is a very, very precise detector, and has a very accurate measurement of the charge through energy deposition into the many active detector the particle goes through, and which allows to identify very well all the nuclear species going through up to iron and even slightly beyond. You can appreciate nickel, hint of cobalt, and also zinc that is not visible on this scale. Very important is our capability to measure to high rigidity, and this requires a constant monitoring of the capability of our spectrometer to be accurate. Okay, this we can do it by breaking our spectrometer in two parts: the green one, what we call upper, and the blue one we could call lower. And we can measure two rigidities with these two parts, and then compare the inverse reconstructed rigidity with a simulated fully aligned detector. And this is the way we mark our rigidity resolution. And also the absolute momentum scale is very important because a shift in the central tracker plane would create a momentum shift of 10% at 1 TeV. And we do this with electrons and positrons because we can measure the momentum in this spectrometer and the energy in the eCal. And then we can compare the difference of these two for electrons in yellow, positrons in blue, and what we do expect. And this is again give us an uncertainty of an absolute scale of 3% and 1 TeV. So this is to give you the idea how accurate the detector is. The other big problem in measuring nuclei is that nuclei interact also with our own detector material. So the actual flux we measure inside our detector is a fraction of the flux entering in the top of the detector. Then we need to understand the cross-sectional interaction of our detector with this material. And we do it using of the detector as to recognize the incoming cosmic ray, and the second half of the detector to see how many times it interacts with. We can do it for upgoing particle and for downgoing particle. Actually, they are side-going because we use the periods where ISS fly horizontal to have also a pressure, relevant flux of nuclei also from the bottom. This two ways measurement of the cross-section combined with the high resolution knowledge of our material allow us actually to measure cross-section. For here, we publish the helium-carbon interaction cross-section as function of rigidity. All these work we have done to understand how our detector behaves in measuring nuclei allow us to produce very, very accurate measurement. You see here the oxygen that we published already some time ago, and that we were able to get up to the TeV, but also, and this is something recent, the fluorine that we published this January, okay, and neon and magnesium that are still preliminary. Now, neon published, magnesium is still preliminary, that we published, we are going to publish very soon. You can appreciate the accuracy of the precision of our measurement as compared with the other measurements available. And this is some part of what we want to do moving forward with the nuclei. Also, here I show silicon for what we collected 1.6 billion of event, sulfur, and more important, iron. I will come back on it later. So the idea, as you know, the nuclei up to iron are produced in the stars, and the heavier nuclei are produced in the supernova remnants, where they also are accelerated. So we try to look if we can see a uniform behavior on the primaries that are supposed to be accelerated at the same place. If we look for the most, let's say, abundant species like helium, carbon, and oxygens, we recognize identical behavior, where in this plot, as you see, we are, as usual, multiplying the rigidity to 2.7 to get the features, and we rescaling the fluxes to superimpose them. If, however, we start looking at the heavier nuclei, which are to be primary, we observe a slightly different behavior with a slightly different spectral index. Flatness means spectral index 2.7, and so you see the heavier primaries seems to be more to have a softer spectral index. Okay. As I was mentioning before, iron is one very important element, because it's the heaviest produced in the stellar evolution. So it kind of mark a step in the abundance of the elements. Elements above iron are much less abundant. What we wanted to look is if iron was behaving as a helium, carbon, and oxygen, or as this second group we spotted as neon, magnesium, and silicon. And what we found is that actually iron seems to be in the same class of helium, carbon, and oxygen, suggesting that maybe neon and magnesium and silicon may have a slightly different story in the acceleration and the propagation, or maybe they have also some kind of secondary component. Secondary component because we know that the primary cosmic accelerated in the supernova remnants, it's impinge on the interstellar medium, and by spallation create what we call secondary cosmic rays, like, for example, lithium, beryllium, boron, fluorine. Here we see again summarized. You see helium, carbon, oxygen, neon, magnesium, silicon, and as expected, the different behavior of the secondaries that kind of flat out at 2.7. And here we see the lightest, like lithium and beryllium, boron, and an heavier secondary like fluoride. We try to compare AMS light nuclei with Voyager, trying to Voyager, of course, is now outside the solar system, and measure the so-called interstellar flux that seem to be in correlation with what we observe, for example, on the proton-helium ratio. That seems to be some kind of continuity. Apparently, also on helium over carbon, and the ratios versus the oxygens. We use the ratio because the ratio are supposed to factor out the solar activity that is very important instead in modulating lower energy fluxes. You see here the expected flux of proton above 100 MeV, and whose shape strongly depends on the Earth's magnetic field. And in fact, you also see here the South Atlantic anomaly that is made of particles trapped in the geomagnetic field. Once we go and look for nuclei, so above protons, we spot a similar structure, of course, without the South Atlantic anomaly. Given the large acceptance of AMS, we are able to produce to measure the proton flux, for example, in a time scale of days. So some instruction how to read out this plot. You see on the radius the flux intensity. As you move from here around the circle, you get the time evolution, okay? And the different colors corresponds to different intervals of energies. So we see that at lower energies, we have the largest fluxes, but I invite you to appreciate how large is the variation of this flux over the almost 10 years in this plot of AMS measurement. Also, on the lowest energy, we can appreciate on top you see of an expected variation corresponding to the almost 30 days Barter cycle of the sun. We saw the effects of major solar events. As we move to higher energies, the impact of the sun activity becomes less evident, and when we are already at 4 GeV, we still see some trace of the largest events, but is different. The interesting thing we can do
4 minutes left.
also
4
yes,
minutes left.
It's okay. Also for the helium flux, where again, in the lowest energy bin, we can see the effect of the solar events. Also for helium, that is, as you know, 10 times less as protons, we can spot the structure of the Bartel rotation of the sun. and so we can explore over the full solar cycle and beyond the fluxes of the proton, helium, electrons, and positrons in a very fine-grained time evolution. Concluding, AMS is measuring with high accuracy nuclear spectra up to iron and probably just above. This measurement reveals new features that are supposed to help in producing a more accurate model of cosmic rays transportation through our galaxy. And AMS also can study cosmic rays, time depth density correlation with sun activity, and so contributing to the space weather domain. AMS is supposed to continue beyond 2021, at least to 2028, and we will use the largest set of data we get also for doing what we have done in the past, like using positrons and antiprotons as probes for exotic signal, complete the cosmic rays measurement, and also search for antimatter and antideuterons. Thank you.
Thank you, Paolo, for this very nice talk. We have the 5 minutes for questions. Yeah, I see a raise hand from Pier Simone. So please, Pier Simone.
Yes, Paolo, thank you for the very nice talk. If you go back to your slide number 6, where you show the amount of interactions in TRD, I'm always been very curious about that. I mean, in this picture, the tomography of TRD, I mean, it's clear that you have many interactions, and I guess that the picture you're showing up on the left is Monte Carlo, I guess, because I don't think you can. Is it right? I mean, you just reconstruct one track, I guess, not the other ones. So my question is,
no, we do reconstruct also the other tracks.
They go.
We use the TRD that has 2 projections. You know.
Ah, you use TRD itself. Ah, okay.
You saw TRD as X projection you see on top and the bottom, and Y projection in the middle. So
yes, of course. No, you're right. So you don't reconstruct in the spectrometer, but in the TRD itself. Okay. So my question is, I mean, the survival probabilities, say, of ions in TRD are. I mean, I've never seen these plots. I've never had the chance. I'm sure you know very well. I mean, what is the probability of interaction? But it is probably not so small. I mean, the amount of material in TRD, I guess, is not so small, right?
Exactly. You're right. The survival probability for helium, that is not that big, is like 60% so on average, let's say.
Yeah.
Okay. So yes, this is a major problem when measuring nuclei, because you have this large correction you have to take into account. That's what we did using this tomography to be sure that our Monte Carlo actually contains the material description that is matching what we observe here. Okay. And the other very important point is what I was discussing here. I probably was too fast. How to get to this survival probability when your Monte Carlo can be trusted up to some level. Okay. So what we did is to actually take I don't know, let's take an iron nucleus or a carbon, let's say, a carbon that you can really well identify by its charge, okay? up to here. And then you count how many times you get a carbon layer.
Oh, this is extremely nice.
And the point
I don't know how much. I don't know how much statistics you had, because I mean, you know, these runs that you have taken with the ISS in horizontal position are not very long, I guess. So I don't know if you have enough statistics to, you know, to measure well.
Good point. Compare. So we have enough statistics for helium, carbon, and oxygen. Okay, and we use these to you know, to prove that our method was correct, going up and going down. Okay, because this is where we found let's say at the beginning inconsistency to be corrected. At the end, when we using this, we were convinced that we were doing a calculation on survival probability in the right way, both going up and both going down in a coherent way. For the other nuclei, which are less abundant, we just use them from the top when flying in the normal zenith pointing direction. And this was our test bench to understand how to be sure that this method was correct. At that point, we were also able to tune the cross-section in the Monte Carlo with what we measured. And as I said, we were at the end also capable to actually perform a measurement and publish that.
Okay, thank you very much.
You're welcome.
We have time for a very quick question from Ivan.
Yeah, very quick. This is related to the same issue. So if you go to the next slide, 12, you show the measurement, I would say, or AMS of this cross section. So we see an uncertainty of the order of 5%. So I expect that this is part of the systematics that will directly go to the measurement of the flux of helium. And this is increasing with energy. And I guess that the systematics uncertainty is even higher for iron, for example, and is energy dependent. So first question, is this true? And second question, why don't you show on this same plot the prediction of the uncorrected, not yet tuned simulation?
Okay, so let's go by in the order. Yes, this is true, of course. This is a systematic effect we account for. I understand your question. We don't have actually the uncorrected simulation, because then we ran the simulation with our updated cross sections. Okay.
In other words, how large is? Sorry. In other words, how large is the correction that you apply to the Monte Carlo cross section after your measurements? 10%, 20%, 40%?
Well, the cross section are tuned and depends on the okay, sorry. Oh, because there's some history. Originally, we were using the standard Jet 4 system, and then we passed to DPM Jet 3. In DPM Jet 3, the amount of correction became much smaller, and the resulting systematic error in the flux, that is what I can quote, is of the order of a few percent. At the end, the systematic error coming from the limited knowledge of the survival factor of the nucleus going through is few percent. This is what I can say.
Okay, thank you. And sorry for the word question.
It's okay.
Okay, so let's now move to the second talk that is from Professor Pier Simone Marocchesi, full professor at University of Siena and NFN, and principal investigator of the Kalex experiment. So we are still on the International Space Station for an update on the results of Kalex mission. So please, Pier Simone.
Yes. Okay, can you see my screen now?
Yes.
Okay, so first of all, I mean, on behalf of the Kalex collaboration, let me thank the organizer for your kind invitation. I will try to go fast through the first slides. The important thing is that, okay, Kalex lives on a very interesting place. I mean, this is an exposure facility of the GEM-EF, so the Japanese module. And the interesting thing is that we have nothing above our head. So we have the ability, let's say, to have very little material to do our measurements. So the Kalex, very briefly, has a charge detector on top made of with this scintillator pedals, a hodoscope with 2 layers, and is followed by what we call an imaging calorimeter, which is a pre-shower made of fibers, scintillating fibers, read out individually. So it's 1 millimeter cross section. And this allows us to make tracking with this device. There are also small absorbers. In total, they make 3x zeros. And so that the electron shower starts in this part. So this is a pre-shower is followed by a deep calorimeter of 27 radiation length and 1.2 proton interaction length. And so this is the, both of them makes 30 radiation length. The calorimeter is a homogeneous calorimeter made of lead tungstate logs. And since it's not compensating calorimeter, we have a very good proton electron discrimination better than 10 to the 5. So schematically, this is, of course, Monte Carlo. You can see that we can take advantage of the tracking to find out if an event is a gamma ray. There are no points on top of a detector. And the electron shower is typically well starting inside the IMC, and then it's well contained in the calorimeter. And the proton, as you know, has a large breadth in width. So the okay, so the fact that we read the charge of the particle on the CHD, but also in the multiple d by dx in the IMC, allows us to measure the charge twice. And do you see the point? Okay. And so you can see an example here on the right, a bidimensional plot where we have on the y-axis the charge measured in the IMC, and the charge in the CHD is on the horizontal axis. And this allows us to have a very nice separation, and you can judge here the discrimination by going through the elemental table of elements. The resolution was actually measured at beam test at CERN, where we used a beam of ions with a fragmentation target. And here, for instance, you get a show of the charge separation that you get for boron carbon, I mean, by 7 sigma. And here you can read the charge resolution, which is better than 0.1 for low energy, so low Z elements, and then it goes to 0.3 for iron. I have to go quicker. So this is just a show of some events from top left clockwise. You have an electron of free TeV, and you see it's still contained in the calorimeter. And then you have the helium 700 GeV deposited energy on the right, and then bottom left, the carbon of 2 TeV and the iron of the 4 TeV. So you see the ionization of the iron is quite strong. A very important point is that we have a very large dynamic range that allows us to measure releases of energy from 1 minimum ionizing particle to 10 to the 6 MIPs. And this is due to the fact that we read the light from the lead tungstate with two different area, with an PD, avalanche photodiode, and a PD of different area. And also we break the electronic dynamic range into two. So we have 4 ranges, and we spend everyday time, let's say, to cross-calibrate and make this seamless transition between these domains. So let me go quickly to the observations. So Kalex is now in space by more than 5 years. And in total, as of April this year, we have more than 2,000 days with a lifetime fraction of 85%. So the exposure with the high energy triggers is 178 square meters per radian day. We run even during the crossing of the South Atlantic anomaly. We get higher rates, of course, but our trigger system is such that we prescale something, and that's fine. And this is the point source exposure for gamma rays. The important thing is that we have a geometrical factor of about 1,000 square centimeters per radians for electrons. And for high heavy nuclei, we have a special trigger we'll show you later that allows us to have 4 times as much. The number of triggers we have collected with a high energy trigger is about 1.3 billion, but since we also take low energy electrons and so on, in total we have collected about 2.7 billion. Now I will go through the main results. The Kalex has been designed mainly for electron measurement as a primary goal. And this is our first publication, actually the second, but let's say on PRL. And here the range went up to 4.8 TeV, where we could detect the flux reduction above 1 TeV. Now we have more statistics by factor 2.3, and this will be presented at ICRC. So we at that time, let's say we observed this flux reduction, and we don't see this big structure that was apparent, let's say, in damp measurements. And so the situation, published situation is this one. We are actively investigating this region above 5, let's say, TeV, where we hope to find the footprints of possible presence of a nearby source. This is again is all embargoes until the CRC. The same thing is for proton. Proton we published on PRL up to 10 TeV, and as you may know, and we have seen clearly the hardening of the spectrum, and so saying in between the energy ranges from 50 GeV to 500 GeV. We can say fit the spectrum with a smoothly changing power law, and let's say the onset of the hardening is actually more closer to 500 GeV than at the lower energy. Of course, there is a large error, but this is what we find. So this is, let's say, up to 10 TeV. This is in agreement with what Dampe has published later. They actually reached a higher energy and showed a flux reduction above 10 TeV. And there will be some important, let's say, update of this at the ICRC. So we can measure the spectra of all nuclei up to nickel and even above, as I will show later. And this is our published result on carbon and oxygen, where we clearly measure a change of the spectral index above, let's say, 200 GeV per nucleon or so. I'm sorry. Okay, I don't stay longer with this. We have some issues about the total normalization of the flux with respect to MS, for instance, but I will not talk about that today. I want to concentrate on our latest paper about iron that came out just 1 month ago, more or less. And here you can see how well, how important, let's say, it is to have a double redundant charge measurement. So here again, here we actually, in this picture, I actually compare the two layers of CHD, and you can see clear separation, for instance, of iron events with nickel and with chromium. So we have fitted this spectra in several slices of energies and compared with Monte Carlo so that we can estimate the background. So since I have little time, I will go to the results. So with iron, this is the measurement of iron published on PRL. And what we measure, essentially, this plot I'm showing is multiplied by E2 with 2.6, because what we actually measure is almost a flattish dependence of the spectral index. And so this is best visualized by multiplying by 2.6. And as you can see, let's say we stop here at 2 TeV per nucleon. And we have compared our result with other experiments with most notably HE6 and CRN and so on. And also, of course, with the AMS, where we see a tension in the normalization. AMS is higher by about 20% with respect to us. And Sanrico is a balloon-borne experiment with the nuclear emulsion. We have normalized our flux to AMS just to see if the spectral shape was consistent. And actually, we find that if we, here, this spectrum is multiplied by 2.7, because MS uses 2.7. And actually, once we have factorized out the problem of normalization, it seems to us that we are very consistent also in shape with AMS. And this also very similar errors. This probably means that AMS has a very hard rejection of events because in the end they end up with a statistics with similar to us. So say our conclusion of this is that we at the moment we don't have the dominated by statistical error, and we don't have the statistical power to test an hypothesis of hardening at very high energy. However, at lower energy, like 200 GeV per nucleon, we actually don't see a sign of this hardening at the moment, okay? We didn't put limits, we cannot, we didn't quantify this, but to say this is the situation. The green part is the systematic error, the yellow part is just, is the total error, sorry. The yellow one is the systematic. We have also a special trigger that triggers, I'll say, on the top of the detectors so that the field of view becomes very large. And this allows us to collect high Z elements, which are very rare, with a much larger, ×4 larger geometric factor. As you know, above nickel, the abundance of these trans iron elements drops down by orders of magnitude. So you really need a lot of statistics. With this high energy trigger, we measure their abundances, where we cannot measure their energy because most of them don't go in the calorimeter. However, we have also trigger, the high energy trigger, where a fraction of them can go inside the calorimeter. So this is the abundance normalized to iron of these trans iron events. And you can see that we go up to zirconium, I mean, because our energy, our charge range actually goes up to Z equals 40 more or less, even a bit more, because we have this very large dynamic range. So this is the situation. I don't have much time, I think, to go through the gamma ray measurements. Certainly Kalex has an effective area, which is by an order of magnitude at least lower than Fermi, so it's not designed for this. But however, we could measure, let's say, the position of the sources, discrete sources, and also the diffused gamma ray background, because we have a very good angular resolution. Actually, at high energy, our angular resolution is even better than Fermi. Our resolution is of the order for gamma rays of the order of 5% and 10 TeV. So here is a map of some identified sources. We also measure their spectrum and compared with MS, but of course, this is not a competitive measurement, if you want. We have a dedicated gamma ray burst monitor that has 2 instruments, and so it can span from 7 keV to low energy gamma rays of 20 MeV. And then also at the same time, we have the calorimeter, so that if you have an event, gamma ray event of higher energy than 1 GeV, we can see it. So we have an ongoing campaign that measures gamma ray bursts, and actually we have seen almost 250 of them so far, and most of them are so-called, if you measure this parameter called T90, you can divide them in long and short gamma ray bursts, and almost 90% of them are long. We also have a follow-up observation of gravitational wave events. We are in contact with LIGO and Virgo. So during the round 3, we observed together, we got the alerts. And but so far, we could just put limits. We didn't see any follow-up event. I want just to mention here
3
briefly.
minutes left.
Yes, I've finished. I just want to mention that we also have a very wide program of observation with the space weather phenomena that spans from electron precipitation. Actually, our very first paper was on this, because we have this, we can measure the count rate on the CHD, which is the first CHD has nothing on top, and so this is very large and accurate instrument to do this measurement. Then we can measure solar energetic particles and also make studies of the South Atlantic anomaly. Now you see this nice movie here that shows that since the start of observation, we have noticed a steady increase in the all-electron flux in between 1 and 10 GeV. And this is because, let's say, in the past 2 years, the flux has reached the maximum that was set by Pamela during the previous solar minimum. So here you can see as a function of time, and this is a 4-Bush decrease and so on. And finally, let's say, but you are not expected to read this table just for your convenience. Let's say we have some reference of the published paper, the reported energy range. There will be a new table with new updates at the CRC. So I am at my conclusion. So Kalex has been successfully launched in the summer of 2015. Now we are more than 5.5 years of excellent performance. the incredible stability of the instruments allowed us to make very nice measurement, I guess. And then the important thing is that we measure the linearity of our energy measurement. This is very important to know your energy scale, and we published the details of this. We do continuous on-orbit calibration especially with the helium nuclei, and the high energy triggers is operational for has been operational for more than 2,000 days with a very large lifetime fraction. And we have more than 2.7 billion events of high energy trigger. So the interesting news is that the operations on orbit have been approved by JAXA to be extended up to the end of the solar year 2024 at least. So we are very happy about this, and please stay tuned for the updates of our analysis results at the incoming ICRCs in 10 days from now. Thank you very much for your attention.
Thank you, Pier Simone. So we should expect more results shown at ICRC on some of the topics that you said during your talk. There are questions for Pier Simone. Yes, Paolo, please.
Yes, more a comment than a question. About, yes, of course, about iron.
I guess.
I think this is this tension is interesting. Okay, and I think we should find a moment where the two collaborations should find a way to confront and try to find if there is something that put us in this 20%. About the statistics. This is not our last word on iron, because we have actually, after a few years of data taking, we realized that our trigger was not optimized for iron, and we were losing a lot of events. So our data extension for iron is of the order of 5 years, five years of actual data taking, and probably less of analyzed data. So just to give you the information that we will come back again, probably reducing the uncertainty at high rigidity, and maybe adding a point.
No, thank you very much. I really hope that there will be some interaction for this question of normalization issue, which is not for iron only, but also for carbon and so on. And you will see for boron, and yeah, in some places we are consistent with Pamela, so it's really something we don't understand. We are using 3 Monte Carlos. I mean, we are using EPICS, Gen4, and Fluka. So it's a bit of a puzzle, and we have to solve it.
Yeah, go ahead.
For iron, since I had little time, I forgot to say that we are using, let's say, a fiducial region. So here we are using 1/2 of the geometric factor, but because we are trying to be very accurate and so on. So let's hope to find. We were very careful in the statement of the paper. See, we don't make any particular claim. We say that we don't have the statistical accuracy here to know if these last points are going up or not. But certainly, it looks to me that in this region, around 200, 300 GeV, we must be a bit careful, because it could well be that you know, the flux here seems quite flat, to be honest. But,
yeah,
but let's see.
We have less accuracy than you, statistically speaking. There, so
see,
we just observe the compatibility with helium, but
see,
you know, we have big errors.
Yeah.
And about again normalization, I think yes, we should discuss, because we found really a breakthrough when using DPM jet, because we observed within our detector with the fragmentation multiplicity. So you get carbon, you look at the fragment multiplicity inside AMS, and this Monte Carlo was clearly superior to the one we used before.
Yes.
So that's something we should discuss. I agree.
Yeah. I agree. Thank you, Paolo.
Yes, of course, this problem of normalization and flux discrepancies, of course, not a problem of IMS or Kalex, but it interests also other present and future experiments. So we need to try to work together in order to solve these kind of discrepancies, both at the level of Monte Carlo, but especially for future mission, to find a way to calibrate the detector during flight operation. That is, of course, not so easy. Okay, there are other questions for Pier Simone? If not, we can move to the third speaker of today, that is Professor Paolo Bernardini of University of Salento and INFN, that will show us the last results of DAMPE. Paolo is an expert of cosmic rays and neutrinos, and he will show us the last results of DAMPE. Please, Paolo. We cannot hear you.
So I had a problem with the microphone. Sorry.
Oh, okay. No, now it's okay.
I found it. Okay, I start with the presentation.
Okay, very good.
Okay, I have to speak about the fluxes of cosmic ray, charged cosmic ray measured by DAMPE. Some result has been anticipated by Marocchesi. Anyway, this is fine. The collaboration is essentially Chinese, a small collaboration. It is promoted by, the experiment is promoted by the Chinese Academy of Science. But there is an important contribution by Italian and Swiss institutions, IUC. The meaning of the name is dark matter particle explorer. So this is okay. This is the outline of my talks. So some words about the scientific goals, the features of the detector, what we did with the beam test, then the performance on orbit, the on-orbit performance, and some result about, I repeat, charged cosmic ray. Don't understand? Okay. About the dark matter, you know that it's possible to find some signature of the dark matter looking for the annihilation of some particular unknown particle, neutralino, for instance. So we need to have a long exposure, a high energy resolution in order to observe such possible signals. We think that DAMPE has the features to search for these signatures in cosmic rays and in gamma rays. So we tuned the design of the detector in order to be sensitive to electron and photons made in this range from 25 GeV up to 10 TeV. But today I will speak essentially about cosmic rays, the other important topic of our project. So the idea is to check if the simple power law can describe the cosmic ray spectrum before the NE. So also to enlarge the direct measurement of cosmic ray in order to put a bridge with respect to the experiments on the ground. So you know very well that this precise measurement by such different experiments are so important to test different models for the source, the existence of the source, the production, the mechanism of acceleration, diffusion, and also the presence of different population of cosmic rays. The detector features have been defined in order to be sensitive essentially to electron and gamma. So we have to reduce to recognize the noise, the background by protons, and this is the rejection capability we need in order to make this search for dark matter signals. And to make this, we need a large dynamical range from few GeV up to 10 TeV. This means that for the single bar of the calorimeter, we need a dynamical range from MeV up to TeV. So to solve this challenge design requirement, we use the different dynos for the readout of the calorimeter elements. This is the sketch of the detector. The mass is around 1,400 kilograms. The power is lower than half a kilowatt. And the lifetime for a synth lifetime was more than 3 years, but now we arrived to more than 5 years of data taking, regular data taking. The elements the detector are 4. We will go in some detail about this part. Plastic scintillator detector, silicon tungsten tracker, BGO calorimeter, and on the bottom, a neutron detector. Few details, I have not so much time to go in detail anyway. For the plastic scintillator detector, this shape, this arrangement is necessary to have a high efficiency, the single layer efficiency more than 95%, and the position resolution lower than 2 centimeters. This is the silicon tracker. Again, no details about the geometry, but you know that in these 12 layers of STK, we inserted 3 tungsten plates as cold photon converter for gamma astronomy. Go to the BGO calorimeter. This is maybe the main characteristics of the detector, because we arrive to 32 radiation length, so it's very deep detector using these 14 layers of BGO bars. I repeat, we read the signal for 2 different dynos in order to cover the dynamical range I said in the previous about the previous slide. The neutron detector, not many words about this. This is the reaction by means of we observe the presence of neutron associated with an hadronic shower in the detector. So this is a review of the four detectors. It's clear that we use PSD as a veto for gammas, but mainly for the charge measuring using the block relation between the energy deposit and the Z measurement. STK used for the precise tracking. This is the resolution, spatial and angular. And we can make also a measurement of the charge looking at the square root of the ADC inside the STK. It's possible to measure the charge also for MIPS, for minimum ionized particle in the calorimeters, but calorimeter is mainly used for the energy measurement using the development of the shower, electromagnetic or hadronic shower inside it. The hadron rejection is possible also looking at the delayed coincidence of neutrons in the neutron detector at the bottom. Okay, this is a sketch about the different topological features of the events. So you see the electromagnetic shower well contained on the left, on the center, electromagnetic shower well contained in the calorimeter, and in the case of gamma rays, you don't observe any signal on PSD. For proton nuclei, the hadronic shower is not contained, is developed, the release of energy is more than 1/3 of the total energy. Anyway, by means of the unfolding, we're able to reconstruct the energy of the primary particle. This is just a sketch, but in this case, you look at real events. PSD on the top, the tracker, and the BGO calorimeter in the bottom. Beam test, we performed a lot of beam tests. We use also argon and lead beam, and we looked at the fragments, but I have no time to go in detail. Some result for the electron energy released in the BGO and the capability to recognize the corrected energy. In this plot on the right, you see the agreement between the energy of the beam and the reconstructed energy on the vertical axis. On the bottom on the left, the elemental spectrum for the fragments of an argon beam. The helium peak has been removed in order to emphasize the other species of particles. And on the right, you see the same peak for different particles with the same electric charge. So that is equal 1, and the shape of the energy deposit is the same for pion, muon, electron, and proton. So this checkup is performed in test beam. This in a similar check for the reconstructed energy for protons. And you see the agreement with Monte Carlo and measurement in the beam test. Okay, we go now to the launch on December 2015, and just a week after the launch, the high voltage was switched on, and the data taking started in few days after the launch. This is some result on orbit. There was a strong reduction of the noisy STK channels after the launch. This is what we are able to reconstruct for the South Atlantic anomaly compared with the AP9 model. So we removed the data in this collected in this area due to the particular magnetic field in this region. And these are some other results for the trigger rate, very stable. The stability of the minimum, the most probable value for the Landau fit for the energy deposit by MIP particles in the PSD and in the BGO. So you see that stability of the most probable value of the Landau fit, and a plot of the regularity, the continuous shape of the dynodes, dynodes 5, dynodes 8 of the PMT readout in the BGO calorimeter. So by means of these two dynodes, we are able to cover a wide range we have spoken before. And another important check of the stability of our data taking, the daily counts and the accumulation, the number of events we got in 5 years, more than 9 billion of events in 5 years. And so you see the regular shape of this increase. Go to the analysis. In this case, we look at the electron plus positron identification. We are not able to distinguish the sign of the charge, but so we select Z equal 1, and we select the events looking at the features of the of the shower, the electromagnetic shower in the BGO calorimeter. We use this plot, this scatter plot, in order to show the difference, the separation between protons and positron and electrons. On the vertical axis, we have the ratio between the total deposit of energy on the last layer of BGO and the total energy collected on the BGO calorimeter. On the horizontal axis, we have a spread. This is a kind of mean spread with respect to the center. I means is the index of the plane. J is the means, is the index of the elements on the plane. So we make this measurement of the spread of the shower on the singular, on all the, is the sum of the spread of the shower on all the planes of the BGO calorimeter. So you see the two populations are well separated, and we assumed this cut, introducing the variable Z, in order to select at around 8.5 the separation between the accepted electron signal and the proton signal. This is a template fit where we have inserted also the Monte Carlo in order to estimate the pollution, the contamination by proton. The quality of this cut was checked in the test beam, so you see what is the distribution of the quantity Z when the beam is just by electrons, and what is the shape of the Z in the case when the beam is by proton. On the bottom, you see some check about the efficiency for trigger and trigger efficiency and tracking efficiency in order to show that the Monte Carlo reproduce the data, the collected data. So this is the result of our electron measurement. You see, Marocchesi said before, but I repeat that we see an agreement with the Fermi-Lat data. We don't claim any particular significance about this peak. Maybe we don't claim anything, but maybe a statistical fluctuation. Anyway, we'll check in the future with the final analysis of this spectrum at the end of our experiment. Go to the fit of the spectrum. The spectrum can be fitted by a smoothly broken power law, and this softening of the spectrum is confirmed with a significance of 6.6 sigma. About nuclei, we are able, by means of the Z measurement, to distinguish the different species. You see, we arrive to nickel, and okay, this is what we are able to do. And in this plot, there is a comparison of the two proton and helium peaks with respect to the Monte Carlo in order, again, to estimate the signal and the background from one peak to the other one. And this is the standard template fit in order to check the Monte Carlo, the pollution, the signal. This is the result published on Science Advanced for proton. Again, there is an agreement with the measurement by ETIC, essentially with the ETIC, but the shape with an hardening and then a softening seen by other experiments, maybe not with the same precision, but we confirm this shape. So Also in this case, the single power law is not the proper fit for our data. This is the
2 minutes left, Paolo.
Okay, thanks. This is the fit with the smoothly broken power law. You see that this value for the hardening and the value for the softening. Also in this case, the significance is good. Is what we get is 4.7 sigma in order to claim the softening we have seen. Helium flux. This is the result published very few weeks ago on PRL, and in this case, this is the spectrum with respect to the energy per nucleon, but also in this case, an hardening is visible, is confirmed, and also a softening is visible. If we go to the same spectrum, but for the total energy, we performed the fit with the smoothly broken power law, and again we have the hardening with this value from the two different spectral index and the break energy, and for the softening we have this other one with a significance of 4.3 sigmas. Okay, if we compare the two results for protons and helium, the structure is very similar, so hardening plus softening. The value of the break energy suggests that the softening energy depends on the particle charge, so Z equal 1 for protons, Z equal 2 for helium, obviously. Anyway, the uncertainty does not allow to rule out dependence on the mass. A combined analysis for the light component of cosmic ray, proton plus helium, will be presented at ICRC and confirm the separated measures for proton and helium. Just one slide about either nuclei. We will present some results at ICRC. Anyway, in this plot, you see what we are able to make about from beryllium up to fluorine, and you see this is clearly the CNO group, the signal for CNO group. This is the template fit for the same species we have in this plot. On the vertical and the horizontal axis, we have the measured by PSD on the different layers. I arrived to the end. Satellites experiment in this moment push the direct measurement closer to the bridge, so there is the possibility to put a bridge towards to the knee, sorry, to the spectral knee, so it's possible to put a bridge towards the ground experiments. DAMP is a very deep detector, so works properly since its launch, and we expect to take data for a long period, still a long period, and then the structure we have observed for the positron and electron spectrum is a spectral break at around 1 TeV, and there is a clear structure also in cosmic ray spectra for proton, in particular for proton and for helium. That's all. Thanks.
Thank you, Paolo, for this nice review on DAMP results. We have time for questions. Any question for Paolo? Okay, so I have just a comment. Also in this case, as you can see, there are some discrepancy on differences on the overall fluxes between different experiments. I don't know, Paolo, if you want to comment about these or about how DAMP takes under control the systematic effects, etc.
Okay, it's clear that we have these differences. You see, in the case of a proton, what is the uncertainty connected to the measurement for the first band of the uncertainty, and connected to the uncertainty of the hadronic models used in the Monte Carlo. I think that the problem of cross sections and simulation is the main question. Maybe it's possible to get an agreement with a correction on the energy calibration, on the energy normalization. You know that the energy is present on the vertical and on the horizontal axis. So what I mean is that the main point maybe is the structure. So we are observing with different resolution, with different value, but anyway, all the experiment observe the hardening, and then also the softening is confirmed. So I think a normalization of energy and more detailed studies about cross-section maybe in the future can solve this discrepancy. We are making a lot of check about our measurement, maybe also the measurement of cross-section we have discussed just a few minutes ago for the comments by Ivan. Some more strict measurement of the cosmic of the cross-section can improve this result and maybe can remove this discrepancy.
Pier Simone.
See, thank you for. But say I'm very puzzled about these discrepancies in normalization of DAMPE, because you have a problem that you are say higher fluxes than our experiments also for electrons. I mean, if you look at the region, for instance, say for proton and helium, even at moderate energies like 1 TeV, okay, you are definitely higher than Kalex, for instance, and if you go a little bit lower than a TeV, you can compare also with AMS, and you are higher. For electrons, you are higher than AMS and Kalex. So the explanation that this is due to the cross sections convinced me up to a certain point, because I mean you see this also for electrons. So there must be something else if it is a systematic error unaccounted for. Do you have any comments on this?
When I spoke about cosmic cross-section, I mean a general question in principle. This difference is well known. We are performing a lot of check about our measurement. We used giant FTFP BERT for the simulation for helium, for example, for protons. Then for high energy, for protons we use the DPM jet with SCMC jet 4, and for helium we used also EPOS LHCEC just for a test, and we didn't find any difference higher than 1%. So in this moment, we can only confirm our results. This is our results. I repeat, we will go on with the check, but we don't have any, okay, the systematics is where you see it, is very large very large is what we have for helium, for proton. But in this moment, we can only confirm our results.
Okay. Okay. One last quick question from Paolo, please.
Yes, still on this topic. How you comment the fact that protons seems very different from AMS and Kalex, while helium is okay in a large band, but the average is on top. If you go to the next slide or something like that. No, yes.
Think about it. I repeat, we don't have any. We have studied very deeply this spectrum, and we confirm this result also with a combined analysis of protons plus helium. In this moment, I am not able to add any more about this discrepancy, disagreement for helium.
In this
Okay.
speech.
Thank you.
Okay, I think we should move to our next speaker. That is Professor Andrei Turundevsky. Okay, sorry for the pronunciation. He's a member of the Skobeltsyn Institute of Nuclear Physics of Moscow State University. He's a member of the Nucleon collaboration, and is also interested in future mission like HERO. And he will show us the latest results of Nucleon experiments. So please go ahead.
Yeah. My report is about the cosmic ray.
Could you please share your screen?
Excuse me?
Could you share your slides?
I'm sorry. Just a moment. Sorry. Yes. Do you see?
Yes.
Yes, please. If you manage to go in a presentation mode, we can see it a little bit larger. Otherwise, we can read in any case.
Do you see?
Okay, now it's perfect. Go ahead.
Thank you. My report is about the cosmic ray or particles spectrum obtained by the nuclear experiment and comparison of this result with ground-based data. The cosmic ray or particle spectrum is a very important result obtained by the nuclear space experiment. The spectrum was directly measured after energies near 500 TeV. The ground-based experiments provide very large statistics, but their results depend on applied models. The nuclear experiment allows to compare results of direct measurements and data of ground-based experiments. The particle spectrum is presented here. The shape of this spectrum differs from the power dependence. This difference is caused by the universal Ni found in the DDT spectra measured by the nuclear experiment and the other space experiment. For example, Dampe and Kalex. The tensor particle spectrum is well consistent with the data from ground-based experiments and Taiga. But I must speak that the nuclear results differs from the Argo and Bajer results. Some words about the nuclear device. A nuclear device consisted of a charge measurement system, carbon target energy measurement system, a trigger system, and small calorimeter. Charge measurement system included for silicon pad layers. The energy measurement system included 6 layers of silicon microstripe detectors. The energy measurements were based on the new kinematic method, kinematic lightweight energimeter. This method has a bad energy accuracy for individual event, but it allowed to construct a light device. The geometrical factor was near 0.2 square meters steradian. The equivalent device was installed on board the Russian satellite resource as additional payload. This circular orbit was solar synchronous. The satellite was launched in December 2014 and operated for 3 years. The main aim of the experiment were measurements of charge composition and energy spectra of cosmic rays up to 500 TeV. This is the charge distribution obtained by the nuclear experiment. We can distinguish abundant nuclei. So, the particle measurements at high energies are limited by statistics. And the results of ground-based experiments, HE6, Taiga, include all particle spectrum with large statistics up to very high energies. It's possible to compare results of direct and ground-based experiments. This is all particle spectrum. Blue squares are a result of calorimeter of nuclear measurements, and blue and red circles are results of nuclear clamp techniques. We can see that nuclear results are very close to HE6 result. Difference is near uncertainty. And we can see the Taiga result. The result of on some results of some satellite experiments are presented too. So this is the Sokol result and proton result and balloon experiment Arctic result. Spectra are not exactly power law. What is the reason of this effect? The difference of the spectrum from the power law can be evaluated by HE6 test. This is HE6 per degree of freedom dependence on the integral spectral index. The minimal value of He square is equal to 2.21. The difference from the power law is significant. Another characteristic is the spectral index dependence on the energy threshold. The spectral index for integral spectrum. For value for threshold equal to 10 TeV is equal to 1.48, and for threshold 100 TeV is equal 1.78. The difference is near 3 sigma. This is the reconstructed spectral distribution obtained by the deconvolution of the difference is present. Thus, we must take into account the universal need in the magnetic rigidity spectra. The first publication of nuclear data about this effect was here. This simple form is presentation of three rigidity spectra: protons, helium, and all nuclei from carbon to cobalt. And for and rigidities more after the break, we use the simple power fit. But uncertainty of this fit of course is large. There it is indices of rigidity spectra as function of rigidity threshold. After the break, difference of proton and helium spectra is small, but nuclear spectra differs nuclear spectrum differs from the light particle spectrum. Of course, this presumption is too simple, but we extrapolated the spectrum by means of this perception. This fit is showed as a black line. This depends very low to results of Taiga and Hawk ground-based experiment. Up to area of the main NEF3 PEV. Maybe the structure of hardening and softening in the digital spectra determine the all particle spectrum for up to the main knee. And it's necessary to investigate the spectra and chemical composition in this area. And another characteristic is the mean logarithm of the mass number. Data of the nuclear experiment are very close to the data of the Argo and Baiji experiment. I have no data from other ground-based experiments for this area. But extrapolations of our data and Argo and Baiji data differ. But our extrapolation is close to cascade data for energies near 1 PeV. It's a very interesting problem. It's a necessary addition to measure cosmic ray spectra and composition of these energies. And general summary. Then the spectrum of all particles was in good agreement with the data from the terrestrial experiments. There were notable differences from the power law. The values of the mean logarithm of the mass number confirm the Argo data for our energy area. Maybe our data on chemical composition at high energies can be used for simulation for expanded atmospheric showers experiment. That's all.
Okay, thank you very much for the update on the results of Nucleon. There are any questions for Andrei? I have just a curiosity. Probably you told it, but I missed it. The Nucleon experiment is still taking data, or it's over?
The nuclear experiment was exposed for 3 years, and the satellite now is not functioning.
Okay, okay, I see. Any other questions? Okay, if not, thank you, Andrei, again. And now we can move to our next speaker. That let me, yes, Felicia Barbato, researcher of Grand Sasso Science Institute that will talk about a future experiment that is HERD. So please, Felicia.
Okay, do you see my screen?
In a while, yes, we can see it. So please.
Okay.
Go ahead.
So thank you, Fabio, for your introduction. Good morning, everybody. Today I'm going to give you an overview about the HERD space mission. So we all know that cosmic rays are powerful probes for physics law in the very high range, in the very high energy range. And as we saw from the results given in this session and also from other discoveries in the recent years, we made big progress in the understanding and in the knowledge of cosmic rays. By the way, there are still open questions about them, like where are they produced, or how are they accelerated to such energies, or also how do they produce, how do they propagate in the galaxy and the universe. So there are many experiments that are giving us a strong hint about the necessity to study the sub-PV region to understand the dominant origin of the need. So our purpose in this moment is to try to give an answer to this question, meaning is the need due to the maximum energy achievable at the source or to the diffusion processes in the galaxy. So we also saw, also in the previous talks, that the current data suggests that the spectra of cosmic rays doesn't follow a simple power law, but we found an hardening that is well established since his first observation by Pamela, and also its implication on the acceleration mechanism. And there is also a claim for a softening where the first strong evidence was given by Dante data. And the HERD payload will extend the energy range of this measurement in order to make a more detailed study of this spectrum. So, given this introduction, the HERD primary scientific goals will include the precise measurement of the energy spectra of cosmic ray individual species up to few PeV, the study of the electrons and photon spectra for GeV up to tens of TeV, and also indirect dark matter search. And finally, we will try to give a contribution to the multi-messenger observation together with other satellites and ground-based experiments. Okay, so about the HERD collaboration. HERD means high energy cosmic radiation detection, and it will be a facility on the International Space Mission. And it will start operation around 2027 to make cosmic ray direct measurement on the Chinese space station. So the collaboration is constituted by institution is mainly constituted by Chinese institution and European institution with a very large contribution given by Italy. Let's give some details about the mission profile. So as I told you, the HERD payload will be mounted on the Chinese space station. And as you can see here, there is the position that it will have on the Chinese space station. On the right side, we have the horizontal section that allows us to understand better the field of view of the HERD payload that will be around plus minus 70 degrees. So in 2027, we are expected to start our operation and to fly on a circular LEO orbit. So let's go in more detail in the payload design. You can see here a sketch of the payload design that is made by shells. We have 4 equal lateral side and a top cover for each detector. So going from the very outermost, we have the SCD, that is the silicon charge detector for the precise charge reconstruction. Then more inside, there is the plastic scintillator detector for the charge reconstruction and gamma identification. Then the green one is the fiber tracker that will allow to reconstruct particle trajectories and make also a redundancy in charge identification. And finally, we found the heart of the hard payload that is made by its calorimeter that will allow the energy reconstruction and the electron proton discrimination. Finally, on one of the side, there will be mounted a transition radiation detector for the calibration of the calorimeter for TeV protons. So the main requirements of the hard payload that are given by the first simulation are about the energy range. You can see that in the gammas we can make a measurement starting from 100 MeV, while for electrons we are in the energy range from 10 GeV up to 100 TeV, and for proton and nuclei we are in the energy range from 30 GeV up to 3 PeV. About the energy resolution, you can see that both for gamma and for electrons, we are at 1% at 200 GeV and almost at 20% for proton and nuclei from 100 GeV up to 1 PeV. These values are going to be almost 2 times better than a dump payload that can be considered somehow a predecessor of the hard payload. About the effective geometric factor, you can see that we have a very enhanced effective geometric factor, and we are going over 0.2 square meters per steradiant in the gammas, higher than 2 square meters per steradiant for electrons, and higher than 1 square meters per steradiant for protons and nuclei. So let's go shell by shell to understand how these subdetectors are made. For the silicon charge detector, we say that it allows the charge reconstruction, and it is made by silicon microstrip, and it will allow a very precise measure of the impinging particle charge. It is decided to be the outermost detector in order to avoid the early charge change interaction in the plastic scintillator detector. Here you can see a sketch, a rendering of how the SCD is made, and you can recognize here ladder of silicon microstrip. Here there is a picture of one of the dump ladder, and the hard ones will be made with the same, let's say, technique. In the more inside, there is the plastic scintillator detector that will provide high efficiency in charge particle detection, so a very high hermeticity in order to allow the discrimination among charged particle and gamma rays. It will also allow the identification of nuclei up to iron, and it will be very highly segmented in order to reduce the backscattering effect of particles from the calorimeter. Up to now, we have 2 versions of the of the plastic scintillator detector, and we are working on both. So we have one version that is made by trapezoidal bars. Each side and the top will have one X layer and one Y layer of trapezoidal bars, while the other one has a different philosophy and uses tiles, staggered tiles, in order to provide a higher meticity and better performances to avoid back scattering effect. Here you can see that we have two pictures about two main measurements that are ongoing. On the left, there is a very long bar under measurement, namely it's 1.5 meters, that is almost double than Dante bars. We were measuring the light attenuation length to be of a factor 2 in 1.5 meters of this plastic scintillator. On the other side, there are tiles under test beam at CNAO where they were reconstructing the Birch saturation. So, moving more inside the detector, we found the fiber tracker. So the fiber tracker will allow to reconstruct trajectories. As for the others, is also made by 4 identical sides and a cover top. We will use 7 XY planes in each side sector and 5 XY planes in the top sector. Here you can see a plot of the residual distribution for the reconstructed tracks to be around 45 micron of precision. And finally, we reach the heart of the Earth payload, that is the calorimeter. For the calorimeter, we will have 7,500 lysocubes with a edge length of 3 centimeters. And this calorimeter will accept particles coming from each side. As said before, we found that the effective acceptance of the calorimeter is above 1 square meter per steradiant with almost 30% of resolution at 1 PV for protons, while it's almost at 2 square meter per steradiant with 2% of energy resolution at energies lower than 10 TeV for electrons. For these calorimeters, we are going to use a double readout system. Each cube will be read indeed in 2 different ways. The first one that foresees this wheel made by wavelength shifting fibers that are then read by an IS CMOS camera, meaning an image intensifier followed by a CMOS camera with a frame rate of that is higher than 800 frames per second. The second readout system will exploit photodiodes with different active areas. One with a low active area for high energy events, and one with a larger area for low energy events. These photodiodes will be read by the Hydra chip, that is a DAQ, a readout electronics developed by INFN. So this double readout system will help in improving both calibration and trigger capabilities, and also to reduce some systematic effect due to the energy scale calibration. So each one will provide a cross check in the energy calibration for the other. Finally, as we said, on one external side of the Earth payload, there will be mounted a transition radiation detector. This detector will be made in this way, where we have a gas detector with a radiator installed directly inside, and the readout anodes are made by GEMS. The reason for using this transition radiation detector will be to exploit, to provide a further further calibration of the calorimeter. And here on this plot on the left, you can see the linearity range of the transition radiation detector that is going from a Lorentz factor of 10 to 3 up to a Lorentz factor of 10 to 4. Once we understood how the Earth payload is done, and of course you will find more details about all the subdetector and the Earth physics in the ICRC talks, we can have a deep look in the Earth potentialities. So we were mentioning at the very beginning the necessity to enlarge, to extend the energy spectrum of proton and helium in order to understand the origin of the NIM. So with the Earth payload, we will be able to critically address the Z dependence or the A dependence of the NIM. Moreover, also here you see a simulation of the boron over carbon ratio measured by Earth payload in 5 years that will extend, of course, the precise boron over carbon ratio to a few TeV per nucleon to determine the propagation behavior of cosmic rays. Finally, there is also a simulation of the iron spectrum because the heavy nuclei will be good tracer of the acceleration site, and so HERD will strongly improve such measurement. Moving to electron and positrons, we also heard in the previous talks about the excess of positrons. And here you can see that there is a simulation of the expected positron-electron flux made in 1 year by HERD. And this extension in the energy scale will allow to understand where the excess is due to local pulsar or to dark matter sources. So in case of dark matter sources, we expect a kink in the plot. And finally, in 5 years, the Earth payload will also be able to recognize whether in the very high energy range there is a bump due to local astrophysical sources, and in this case we can have a strong hint about the astrophysical nature of this excess. One more objective of the Earth payload is to observe the gamma sky. In this case, the Earth payload will extend the Fermi-Lat catalog to the higher energy, and it will increase the chance to detect rare gamma events. So our target will be to search for dark matter signatures, to study galactic and extragalactic gamma sources, and also gamma diffuse emission, and also finally the detection of high energy gamma ray burst. So just to summarize something about the HERD mission, it will be a space mission that is now being designed, and it is a result of an international collaboration among several Chinese and European institutions to make cosmic ray direct measurement at the highest possible energies with current technologies. So the HERD primary scientific goal will include, as we say, the extension of the measurement of proton and helium flux up to few PV, testing the theory of the knee structure as due to accelerator limits. Then extend the measurement of the electron-positron flux up to several tens of TeV, testing the hypothesis of the expected cutoff at high energy to distinguish between dark matter or astrophysical origin of the positron excess. And finally, the large acceptance and high sensitivity to gammas up to several hundred of GeV to search for gamma line associated to dark matter annihilation, and also for a gamma sky surveys up to very high energy. So thank you.
Thank you, Felicia, for your talk and this nice update on HERD status. We have time for questions, so any question for Felicia? Just if you would like to comment on this. HERD probably will be one of the first mission of these sites to use silicon PM instead of PMT for the readout of scintillating detectors, both in the PSD and in the Viper tracker that will use instead CPM arrays. Do you have any comment on this? Do you expect main difference with respect to, let's say, standard photomultipliers? Some risk on this?
Of course, using silicon photomultipliers will help from a technical point of view, let's say from the power consumption point of view, because if you imagine to make such a large experiment in space with PMTs, it would be very power consuming. So probably there won't be a chance to make such a large experiment in the traditional way, let's say. Moreover, how to say, the pixelated surface of the CPMs will allow also to obtain very high dynamical range, and so to extend to enhance the capability to recognize charge up to iron. Up to iron, for example. And of course, this is a big challenge because it would be the first time that these CPMs will fly, but I think that in the last years, the silicon photomultipliers technology is progressing very quickly, and also they are going to be used also on accelerator, on particle accelerator, where the radiation is a big issue. So I think that by the time that HERD will fly, we will be safe from this point of view.
Okay, thank you, Felicia. Any other last questions? Pier Simone.
Well, I have a comment about silicon photomultipliers. I mean, it is true that they have been extensively tested on ground. I mean, they are on the market, let's say, it's almost 20 years now. However, in space, I mean, we don't have much experience on their performance over very long periods. I mean, you know, they are solid state devices, and of course, radiation damage has been studied, but in some sense, this is the first time they would be employed for such a long time. So I think tests on the behavior of silicon photomultipliers on long duration are important before the mission starts.
Yes, of course, we are not going to launch the detector without testing it longly and widely. We will provide, of course, space qualification and accelerated damage test on the silicon photomultipliers. So it will be something very important also to have an Italian company on our side in order to facilitate, let's say, the communication, the feedback, and so the progress in order to avoid radiation damage.
No, I am not worried about space qualification tests. I mean, yes. These are robust. I mean, you don't break them in any mechanical way or whatever. The problem is that the industry, they have no idea how to make, let's say, very long, very intense radiation tests. Okay, so you have to rely on the experience of people at CERN in the LHC and so on, but still and on radiation damage. Of course, in space, radiation damage is not so important than in LHC, this is for sure. But still, the problem is that I don't expect them to break down, but to need a continuous calibration because their performance can change a little bit. I don't know. I mean, I'm just saying that we have to watch that, okay?
Yes. Yes, if I comment, I agree with Pier Simone comment. I mean, the silicon PM for sure will need a monitoring during all the lifetime of the mission, both for radiation damages, both also for temperature variations, etc. So is a powerful but very sensitive detectors, and so needs to be fully monitoring during all the time of the mission.
Yes, yes. Thank you.
Yes, John, please.
Good morning, everyone.
Good morning.
Yeah, just to follow up to answer or to put some thoughts into what Pier Simone said, is that there have been some missions from Naval Research Lab on satellites with SIPMs that do show enough degradation due to the radiation damage from trapped particles in orbit. There are also a number of experiments, BurstQ being one that will go up soon. Now, these are SIPMs that are attached to, blocks of scintillators, cesium iodide, as opposed to imaging. But there's also Georgia Donalfo at Goddard has a neutron camera, where basically she's using SIPMs to read out scintillating fiber. And I believe some of that may have been, I'm trying to remember if that was in this Inca experiment that went up already or not. But there's another path, if you will, in the future for being able to test the performance of these in space. So just to say that there's other programs going on besides the implementation done by HERD.
Thank you. Okay, I think now it's time to move to our next.
Fabio, ti sei mutato.
Sorry, I pushed the wrong button. So it's time to move to our next speaker, that is Dr. Esteban Roland, member of the HE experiment and researcher at the Centro Atomico de Bariloche in Argentina, that will show us recent results of HE. So now we move on a ground experiment after all these satellite experiments. So please,
yes, okay, good morning. Well, my talk will be then about the cosmic rays at ultra-high energies, and in particular about the results that were obtained by the Pierre Observatory. As you know, at these high energies, there are many questions we'd like to answer, and in particular, we'd like to know what are the different particles contributing to the fluxes and ultimately identify their sources and how they get accelerated to such enormous energies. And also understand what is the reason behind the changes we see in the spectrum and in the composition of the cosmic rays. We would also like to know how the particles propagate up to us, how they are affected by magnetic fields and by the interaction with the radiation backgrounds, and whether neutrinos or photons, for instance, get produced in these interactions. And we would also like to use these particles, which are so energetic, to study the hadronic interactions beyond the energies reached by colliders. And the main observers we have to do all this is the spectrum of the particles, their composition, and the anisotropies in their radial directions. So regarding the spectrum, you know, it's essentially a power law measured from GeV up to 10 to the 20 electron volts. And in this range at high energy, we identify several features like the knee, the second knee, the ankle, and the final suppressions. And in this talk, I will focus about the highest energies that maybe you think as the foot of the spectrum. And at these energies, the fluxes are very low, so only few particles arrive per square kilometer per century. So we really need a huge detectors to measure them. And this was the motivation to build the Pierre Auger Observatory, which is covering 3,000 square kilometers and is located in the west of Argentina. And it looks at air showers and studies both the fluorescence light emitted by the shower particles and sample the particles that arrive to the ground level with these surface detectors. It has then a hybrid concept. The water sharing of detectors of the surface array shown here has 12 tons of water, and the main array has detectors separated by 1.5 kilometers covering the whole surface, and then there is an inner, what we call the infill array, which has half the separation and is sensitive to lower energies also. Inside this array, there are also buried scintillators, which allow to measure the muons of the showers. And the fluorescence detector consists of these 4 sites with 24 telescopes like this one. And in this region, there are also 3 high elevation telescopes looking up to see lower energy showers. And there is also in this region an engineering array of radio detectors. This is an example of a shower that is observed in high remote, both by 2 telescopes in this case and by the surface array. So from the signals on the ground, one can reconstruct, for instance, the core location of the shower and study how the signal changes as a function of the distance from the core. And we use the signal at 1 kilometer from the core as an estimator of the energy of the showers. From the telescope, one can reconstruct the energy deposition along the atmosphere as a function of the depth. And from this, we get both the location of the maximum of the shower, which is useful to understand the composition of the particles, because lighter particles are more penetrating than heavier ones. And then the integral of energy deposition gives us a measurement of the calorimetric energy of the shower. From this, we can calibrate the surface detectors and use this calibration for all the events detected by the surface detector. So the water Cherenkov surface array has a 100% duty cycle. The main array is fully efficient above 2.5 ex-electron volts. This is 10 to 18. For showers within 60 degrees of zenith angle and above 40 eV for more inclined showers. And for instance, for the vertical spectrum, we call this vertical, we have by now an exposure of 60,000 kilometers square years per radian. And for the studies of anisotropies at the higher energy above 40 eV, we use events up to 80 degrees. And by now we have an exposure exceeding 10 to the 5 kilometers square years per radian. And this is a plot of the exposure since we started in 2004. It's a function of time. We are now here. And it's compared with previous experiments and with a telescope array, which is in the northern hemisphere. So the smaller infill array is fully efficient above 0.3 eV for shower with these zenith angles, and eventually allowed also to go down to 0.1 eV to study the spectrum and the large scale anisotropies. The fluorescence detector have a duty cycle of only 13%, the clear dark nights, and is used for many different measurements. This is the result of the vertical spectrum, which was obtained recently, and from it we see very clearly the different features. So this is the Angle energy. We see then the suppression at the highest energies, starting at around 46 eV, and then we also identify this new feature is kind of inflection at around 13 eV. We also measure the spectrum in different declination bands in the sky, and we see no dependence with the declination, so it's quite uniform across the sky, the spectrum that we measure. This is a combination of different measurements. In black, you have the one I just showed about with the vertical events. Then we have the spectrum measured by using the inclined events between 60 and 80 degrees. The infill spectrum going down to 0.1 essentially, and then this in green, the spectrum obtained with the Cherenkov radiation from the air shower measured by the telescopes. And so here you see the second knee also clearly. Regarding the study of the composition through the measurement of the maximum of the shower, this is an example of a shower with 30 ex-electron volts, the dots, and is compared with simulations assuming different primaries. And in blue you have, for instance, an iron simulations, in red different proton simulations, and also you have photon simulation, which are more penetrating even. And so besides the location of the maximum, it's not also important the fluctuation you expect, because for instance for protons you have this different large fluctuation, while iron are a kind of average of many lower energy shower from the nucleons, and so they fluctuate much less. And these are the results we got for the average X max, the location of the maximum as a function of energy, and the fluctuation on X max. And here they are compared to expectations for pure protons or pure irons, assuming different hadronic interaction models. And you see that the measurements go from some intermediate composition to a light composition at few eV, and then it becomes change the slope and becomes increasingly heavier. And the fluctuations here are consistent with a light composition and then go towards very small values. And it's important to keep in mind that you can get a large fluctuation not only from a light composition, but also if you have a mixture of different elements with different values of average X max. So the mixture will have larger fluctuation than the individual ones. And so this is indicating that there is little admixture of different mass components. This is transferring this measurement of X max to measurements to the inferred logarithm of the mass of the particles. And you see that they go to light component in between proton and helium at few eV, and then it becomes increasingly heavier and being at the level of nitrogen or even heavier, depending on the hadronic model you consider, at the highest energies. We also infer X max from the surface detector using the detailed study of the signals on the detectors in the ground, because this is the time trace of the shower in one detector, and you see that there are contributions from muons which arrive early, fast, directly from the production point, and the electromagnetic contribution is more wide in time because particles come somehow diffusing in the atmosphere. And so measuring the rise time of the signal, you can know how many muons and electromagnetic components are in the signal. And more penetrating showers give more electromagnetic contribution in the ground. And so from this rise time, you can infer what was the location of the shower maximum. And since we have much more statistics with the surface detector, we can put more beams at the highest energies. And we see that this trend toward heavier composition persists even at the highest energies. So from this measurement of the spectrum and of the composition, you can try to infer what could be a scenario, possible scenario for the sources. And this is what we did in this work. So putting a scenario with identical sources distributed uniformly in the universe with a combination of different elements, which essentially have a power law and then an exponential cutoff, which depends on the rigidity of the particles. We fit both the spectrum and the composition, and we get essentially this kind of results that the spectrum has to be very hard at low energies, typically e⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ rigidity of few exavolts. So this suggests that this highest energy suppression is not due to the usual GCK attenuation of the protons in the CMB, but is rather a cutoff at the sources. We need a low energy cutoff in order not to have too many light elements at the highest energies, and we need a hard spectrum in order not to have too many heavy elements at the lowest energies. Alternative possibility will be to have a spectrum more like E2-2, and that this steepening, this suppression of low energies could be an effect of propagation due to a diffusion in magnetic fields in the universe, for instance, that will suppress the low energy particles. So being cosmic rays charged particles, they are clearly affected by magnetic fields, both in the galaxy as shown here and outside the galaxy. And for instance, at 1 eV, you will expect that the proton will have a very convoluted trajectory, and it's very hard to do astronomy, but eventually at the highest energies, the deflection becomes smaller and smaller, and you may eventually be able to do some astronomy. And astronomy can help to understand the origin of the cosmic rays, and you have two kinds of anisotropies, essentially on large angular scales and on small angular scales. Angular scale anisotropies may arise from different reasons. One is that the distribution of the sources may be anisotropic and have a dipolar distribution that will reflect on the radial direction of the cosmic rays. Also, you may have an individual source, and if the propagation is diffusive, you will not see localized excess, but a large scale excess. And they can be present at all energies in general. While localized anisotropies on small or intermediate angular scales may appear at the highest energies if the trajectories become straighter. And so this is the result we got some time ago on the large scale anisotropies in different energies, above 4 ex-electron-volt, using the main array up to 80 degrees. So in this way, we cover 85% of the sky, as you see in this map. And we obtain the different components of the polar distribution, the equatorial one, the one along the rotation axis of the Earth, the total amplitude and direction, which are shown here for different energy beams. And the most significant result is this modulation above 8 eV, which is shown here, corresponding to a perpendicular dipole of 6% amplitude, which is at the significant at the 6 sigma level. And the total dipole in the sky has a 6.6% amplitude pointing in this direction of the sky, which is shown here. If you look at the different energy beams, the amplitude of the total dipole increases with energy, and almost linearly. And this is also consistent with expectation from scenarios in which you have sources distributed with some density in the local neighborhood, extragalactic neighborhood. No? And the direction of the dipole in the different energy beams is shown here with one sigma contours, and you see that in all the beams, they are in this region of the sky, which is far away from the galactic center, so more than 120 degrees away for the dipole of 80 eV. And so this suggests that the origin of this dipolar anisotropy is extragalactic. So what could be a scenario that could explain these results? So you know that the distribution of galaxies in our local neighborhood within 100 or 200 megaparsec is not isotropic. Particularly, this is the direction toward the dipole observed in the IRAS distribution, which is not far from the CMB dipole, which indeed is due to the fact that we are falling toward this excess of matter in this region, and we see the dipole. In the same way, one would expect that in this region there could be more cosmic ray sources, and so this should produce a dipolar anisotropy in the cosmic ray distribution at the highest energies. And one thing that is important to take into account is that the galactic magnetic field will affect the dipolar distribution. So if you have a dipole outside the galaxy, and you look it from Earth after the particles have entered the galaxy through the magnetic field, you will see that the original dipole direction is shifted, and you see it in another direction depending on the energy you consider. And so a dipolar distribution in this region will naturally be moved towards this region here, which corresponds to the outer spiral arm of the galaxy. So you see all this half of the sky is focused toward the outer spiral arm, while the other half is focused toward the inner spiral arm. So the fact that we observe the dipole in this region can be naturally explained in these scenarios. We also extended the study of the dipolar anisotropy to lower energies using the infill in particular, down to 0.03 eV. Here we don't have significant measurements of the amplitude, we just get upper limits of the level of 1 or 2%. But we also observe that the phases of these modulations are all more or less aligned with the location of the galactic center. So this was, and also are consistent with measurement by IceCube, IceTop, and Cascade Grande at lower energies. So this was
3 minutes left.
Okay,
3 minutes.
So we have a galactic origin down to about an eV or so, and then they become extragalactic at the highest energies. So on smaller angular scale, we look for excesses, say, scanning on the energy threshold and on the angular scale. And the most significant excess we got was about 38 eV on 27-degree radius, so a large angular window. And this region is particularly interesting because there are many interesting potential sources like Centaurus A or some starburst galaxy, which just lie inside the region of the excess. We also made a cross correlation with different possible catalog of extragalactic sources like starburst galaxies, AGN emitting gamma rays observed by Fermi, or all the galaxies in Tumas, or the X-ray galaxies from Swift. And in all cases, we see that the statistics has a peak somehow around 40 ex-electron volt associated to this excess around Centaurus A, and also show some peaks around 60 ex-electron volt. And then by now, this excess, the most significant one is larger than 4 sigma, but to say something more definite, we need more statistics. Another thing we have looked for are neutrinos. In particular, we can look for neutrinos looking at very inclined showers close to the horizon. In that case, if the shower was hadronic, it would have interacted very far away, and all the electromagnetic component will be absorbed. You will only see kind of bump associated to the muons, while the neutrino can interact anywhere in the atmospheres, and if it interacts nearby, you will see the electromagnetic component contributing. And so we look for this kind of young horizontal showers. We don't see any, and so we are able to set some constraints in the fluxes, which are starting to test some of the model predictions shown here under our bounds. We also look for neutrinos at the time of the neutron star binary measure observed by LIGO. We were very lucky in this case because just the event happened when our field of view was just 1 degree below the horizon, so where we are more sensitive to neutrinos, but we didn't see any, and we were able to set these bounds on the fluxes, which compare with expectation from the different models shown here. And we are above, but not very far away. So there are chances we may see some events of this kind if they are stronger. We also look for neutrinos in coincidence with the blazar Texas observed by IceCube, and we didn't see any either. So for the future, we are now making an upgrade, which is going on very well and expected to be finished by next year. We are putting an additional scintillator on top of the water Cherenkov detectors. We're also putting radio antennas in all detectors. And so we'll have much more information on the showers. However, this we may be able to separate on an event by event basis light and heavy components, and this will be helpful to do astronomy with the light components which are less deflected, and will allow us to study many other things about hadronic interactions and things like that. And so we hope to learn, continue learning during the next years with these upgraded detectors. Thank you.
Thank you. Thank you very much, Esteban, for these interesting talks. We have time for some questions. Could you please comment on the systematics that you have in HE and how these are related on the models that are behind them in order to be properly evaluated?
Which kind of systematics? We have you refer to the spectrum, to the...
Yes. To the spectrum.
Yeah. So yeah, I show, for instance, here the different results from different samples of events, and you see that they are overall consistent, but there are some differences on the fluxes, and these are expected to be related to, say, a few percent shifts on the calibration of the energy. So different samples are calibrating in a different way. And so you need some shifts on the energy to make this coincide exactly. So these are within our systematic uncertainty, the shift that you need to make them consistent. Also, I didn't show it here, but there is a difference between our spectrum and the one by telescope array, which in part may be due to a different calibration. There is another thing that the telescope array has different spectra in different declination bands. So their spectrum in our side of the sky is more consistent with ours than the overall spectrum. But it still requires an energy shift of the order of 15% between the two experiments. But there are studies on this kind of things, and does this answer your question? Or
Yes, yes. Thank you. Thank you. You answered my question. Any other questions? Okay, if not, we can move to the last speaker of today, that is Dr. John Krzyzmanich from University of Maryland, that will talk about a future experiment, that is the POEMMA experiment.
Okay, good morning. Let me turn on my video too, so you can see my pretty face.
Good morning.
There we go. Maybe I should have combed my hair a little bit more. But in any event, so I think I have my screen shared. Can you see it? Let me try to go into full screen here. Sometimes it works or not. Can we see it in full screen?
Not yet, it is black.
Okay, so let me go back and do it this way. I have problems with my Mac, so let me do it, share the screen this way. So, okay, let me expand it a little bit. We okay?
Yes.
We are okay, yes.
Okay, so let's start. So first of all, I'd like to thank the organizers for inviting me and Poema to give this talk. So Poema is a probe of extreme multi-messenger astrophysics. It really is designed to study ultra-high energy cosmic rays and ultra-high energy neutrinos at an energy scale above 20 eeV, using, kind of showing here is the stereo air fluorescence technique to measure extensive air showers. We also have, and what's shown up here on this plot is just kind of a sky map of the test statistics with a hypothesis that starburst galaxies are the cause of at least a portion of the population of UHE6. Also, too, we actually can point at the limb and then look for upward going air showers in the Cherenkov from neutrino-induced, primarily tau neutrino interactions in the Earth. And therefore, what's shown on the bottom plot is kind of giving which we have really good sensitivity to transients. And what's on the bottom plot is shown kind of the distance scale on the left plot for the Fang and Metzger binary neutron star merger model. This is the distance to detect one neutrino, and then a short transient model by Katera et al. So just really what we're talking about, we're measuring air showers, and then just to put these pictures up on top, we run in two different modes, one in Poema stereo, where we have the instruments tilted to view a common air shower and therefore do the stereo fluorescence technique to get really accurate reconstruction of the shower. And then also we can tilt to the limb where we enhance our UHE-CR acceptance with the slightly degraded performance, but we have sensitivity to seeing air showers coming from tau neutrinos in the Earth. I just give you a quick outline there also with a link of references to the various papers we published in PRD and JCAP. So Poema is really was one of the NASA probe studies chosen to define the probe class for the decadal review. And it's really a community effort. We have more than 70 scientists that have been working on this for a while in terms of Al, Jem Yuso, Thier, Auger, and then also in other fields such as Veritas and CTA. But the PI is Angela Linto at University of Chicago. I'm deputy PI, and I just put the list of the collaborators here from our latest paper that details the instrument published in JCAP. Okay, this is built upon a long history, starting back in the 80s with Yoshi Takahashi's mass idea. We're putting basically a imaging detector in orbit to measure the fluorescence. And it's gone through, you know, the early in the 2000s with the OWL study, and then followed by the work that's done in USO, including work a couple balloon flights that have been flown, many USOs currently on the space station. So that's actually testing the photodetector modules that we plan on using at Poema. And there's also going to be a coming up in 2023, a USO SBB2 flight where there's actually going to be a Cherenkov camera with SIPMs on it. You kind of saw this before in the previous talk. I'll go quickly. We're, you know, playing the idea that the features of the cosmic ray spectrum are kind of a lag. We know that we have changes in spectral index that indicate underlying astrophysics, such as the knee. It may be galactic sources Peter cycling out. There's the ankle. But we're really interested at the end. Previous speaker said at the foot. Maybe if we get more precision and a better magnifying glass, we maybe even be able to see toes and actually maybe even bunions in the spectrum if you want to go along with the anatomy references. So this kind of goes it up, and it just also shows too in the previous plot that if we go with more precision or accurate measurements and better statistics, more features are coming out. And I know earlier today, Pierre Simone gave a talk on Kalex showing those that are happening at lower energies with direct measurements, but you also see these in indirect measurements. And one thing, this kind of reinforces this plot on the bottom, showing what the kind of thoughts are you saw from the previous speaker in regard to the composition, the nuclear composition of cosmic rays at the highest energies, is that remember that we're measuring this in an air shower, which is showing up. So the depth of X max gives you, if you will, a measure of how to do this composition separation. But unlike direct measurements where you can get very accurate measurements on the elemental scale, we tend to measure in groups. So proton, or hydrogen, helium, oxygen, and iron, and there, because those four are about equally separated in this X max, and it's fairly straightforward. If you measure this depth accurately, you can at least reconstruct a composition in these groups. So just briefly, what we know about from the current measurements, the sources are still unknown. We saw, I will not talk too much about HE. We had the previous discussion there, but in the Northern Hemisphere with TA, we have the so-called hotspot shown here with a significance over time is somewhat growing in terms of intermediate scale anisotropy. Furthermore, we know that the spectra are different in the Northern and Southern Hemisphere. The blue is shown here in this selection measure from HE. TA is shown in the red. And so this begs the question of getting an instrument that can measure in a single experimental formulation both northern and southern hemisphere sky, and therefore have the common set of systematics to that one experiment. So what we're talking about is basically, this is kind of giving the exposure history of compared to where things will be in 2030, where we plan where Poema was earmarked to be launched. So nadir is this precision, or this accurate stereo fluorescence mode. LIM is the one we're pointing, and that shows you the benefit of going to space, if you will. And I want to point out the bottom plot. This is the instantaneous, they call proton aperture, if you could think of the geometry factor. And that shows where 10 to the 6 kilometers squared steradians are in that in terms of Poema, both in the stereo and the mono pointing. It's showing that, again, that the ability to get exposure over a short amount of time is benefited from going to space. So our goals are to really discover the origin of ultra high energy cosmic rays by accurately measuring the spectrum composition and sky distribution. And this requires very good angular resolution, energy resolution, and X-max resolution. That's why I went to stereo fluorescence. And for free come ultra high energy neutrino measurements via stereo corrections. We're also going to do looking for tilting at the limb. We can have it reduce the energy threshold by the Trenkov to go down to about 20 PeV to search for neutrinos from transient events. And this requires a little bit different in terms of the timing, about 10 nanoseconds, which I'll explain in a bit. But this also, we have, we still have operation of UHE with slightly degraded performance while we're doing that. And again, there's a wealth of secondary physics, including measuring the proton air cross section at square root of S, about 450 TeV. So what does the instruments look like? They're basically large Schmidt telescopes. And I just highlight here that we have 2 telescopes, each have about a 4-meter diameter mirror, a 3.3 meter diameter collector plate, and about a 1.6 meter diameter focal surface, with 45 degrees field of view, and with instantaneous field of view about 0.84 degrees, or about 1 kilometer on the ground. You could think of from 525 kilometer orbit. And the point being about this is very crude imaging, so we're about 10 to the 4 away from the diffraction limit. So really, it's generous to call this a telescope. It's more like the things that you would see in maybe a microwave dish in terms of what's the needed performances in terms of the imaging, i.e. it's not at the capability of, say, the Hubble telescope. What's shown here is the effective area on top as a function of field of view. You could see that light collection is the important thing here, that we get, at least on axis, nearly 6 meters squared, falling to about 2 at the edge. And then also too, that the optics have a really good point spread function, which helps us in terms of the pixel size, and then to optimize the energy threshold of the instrument. So we've gone to the focal plane as a hybrid focal plane, which is optimized for the 2 types of measurements. The majority of it is, like I said, are these PDMs that are being developed for USO. And for the fluorescence, you want to be, in the 300 to 500 nanometer range where the majority of the signal is, and you want a sampling time about 1 microsecond that optimizes the signal crossing a pixel. For the trunk-off, you have to expand the energy or expand the wavelength band, which I'll show in a minute, and you need a little bit more fine timing. And so this is the portion up here that we'll be viewing near the limb of the Earth when we're tilted towards it. And this kind of gives you the reason why. And so the middle plot is really showing the inherent variability from simulations of the Cherenkov spectrum and intensity for 100 PeV upward going air showers as a function of the Earth emergence angle. What is happening is the atmosphere severely attenuates this and shifts it down. You end up coming to a point here where the bottom part is where the ozone kind of cuts you off. But anyway, this motivates the use for SIPMs. And this plot here just says that this kind of details why we're shooting about 10 or 20 nanoseconds. What the mission looks like is going to be a dual launch. This is shown in the dual manifest Atlas V. The parameters are here, but the most important thing is we're able to slew really quickly, and that comes for free with the avionics in low Earth orbit. It takes us 8 minutes to go 90 degrees, and we have enough propulsion that we could bring the satellites together to bring them in the Cherenkov lake pool if we want. And depending on how fast we do that, we could do it so many times Roth per the mission lifetime, of the order of 10 if we want to do it for 3 hours. If we want to wait 24 hours, we can do that about 90 times. So as I said, the important thing is the angular resolution. This is shown here. We're using the stereo technique where there's a plane defined for each detector where that plane crosses a line. And you could geometrically reconstruct the air shower very well. The left plot shows the simulation event at 50 EeV, where one of the lines is the actual Monte Carlo truth, one is from the reconstruction. And the bottom line, this leads to very good angular resolution, which I'm showing here at 40 EeV. In the zenith, we're at the level about 1.5 degrees, which improves as energy goes up, and less than a degree for the azimuth resolution. And why this is important is because this is going to allow us to get very good angular resolution and a very good energy resolution, very good composition resolution, because we're reconstructing the air shower so well. Even though you may argue that for charged particle astronomy, you don't need that angular resolution because the particles bend, at least for reconstruction to shower you do. And so what I show in the left plot is now just showing how well we do in terms of kind of an exposure plot over 5 years for POEMA compared to what was reported in OJ for 2019. On the left side, right side is was for TA at the ICRC 2019 in terms of increase in performance as a function of energy, and then also a simulated spectrum, what would look like with 5 years of with POEMA performance on the right side of it, for assuming both either the TA or the OJ spectrum. In terms of, this is a study that was done by Michael Unger for in terms of the composition with that inherent really good Xmax resolution based upon a model of just extending OJ measurements. In terms of the left, it's just showing Xmax, and then the sigma on Xmax showing to the right, just showing that we have the potential of really extending the composition measurements of the ultra high energy cosmic rays up to higher energies, because we do have the improved statistics, and now with the capability to be able to do that. We also have full sky coverage. The left plot just shows the variability of different energy scales on the sky. But the right plot's important. It shows that different energy scales, what we have in terms of 19.7, 10 to the 20 EeV going up in energy, compared to what's going to be performed by OJ and also TA at this time scale of 2030. So this just shows that we have full sky coverage for ultra high energy cosmic rays through the fluorescence. This leads to kind of studies that you've seen in the previous one with testing various hypotheses in terms of whether the sources of the cosmic rays have a certain percentage associated with, say, a starburst galaxy, doing that analysis with a certain assumption on the angular spread. And the results shown here, the OJ motivation is shown up on top from, at least from the ICRC, and I believe in 2019. And then what we're saying here on the right plot is just looking at how we do with the various test statistics in terms of different assumptions on that based upon the simulated data set. We have 1,400 events in 5 years for the sample, and then a comparison to different catalogs. So the left catalog is the Starburst Galaxy. This is a 2 mRNS catalog sitting here. And what this shows here, based upon what your different assumptions are in terms of which catalog, which fraction of the ultra high energy cosmic rays are from starburst galaxies. You can lead to a test statistics based upon that, and then a number of sigma to make that association. So the goal, so this is just reinforcing why the goal we have is to identify the source of cosmic rays. Also, too, we have ultra high energy neutrino performance. And this is just because with this good angular resolution, we could really tell when an air shower happens very deep, and this is through fluorescence. We have the very good angular resolution, and therefore we can cut, and the right plot just shows the distribution of background cosmic ray events. The conservative assumption they're all proton, that we make a cut at a certain depth, and we could basically eliminate that background and have a pure neutrino sample. Doing that, and with fluorescence, just to remind you that we're sensitive to all 3 flavors. It comes a little bit differently. For the electron-neutrino interactions, we see 100% of the energy in the air shower through the charge current. For the muon and taus, we assume we only see the hadronic system, which is about 20%. The gamma C tau is way large for tau leptons at this energy. We assume it skedaddles out of the field of view, and the muons we assume, because its air shower production is lower, we don't see it. It's a conservative assumption, but we're also sensitive to neutral current interactions too for all 3. And so the end of the day is that you end up with a sensitivity curve here for 5 years. And again, I want to reinforce these measurements come for free, because they're doing this when we're doing stereo UHECR fluorescence mode. And you can see where our sensitivity is in 5 years for Poema compared to what is there. And in particular, starting to go into sensitivity to these objects that are thought to potentially be early in the universe, the so-called, the neutrino flux moduli fields that potentially have been happening that potentially existed very early in the universe and could lead to a source of very high energy neutrinos. Now moving on to tau neutrino detection. So basically what you do is you're using the Earth as a neutrino and a tau filter. Neutrino interacts, and therefore the energy coming out depends upon, if you will, the angle, the so-called Earth emergence angle. And this shows that this is for actually a flux of, assuming a cosmogenic flux of neutrinos. But you can see what happens as you go through more and more Earth. It's not really true Earth skimming anymore, because we want to actually use the enhancement of the regeneration to repopulate, right? We want to see as taus decay in the Earth, they decay into neutrinos. Those could reinteract with regeneration. We could see the net effect that we end up having fairly decent flux of very low energies, which you can observe in the Cherenkov radiation because it's beamed. And this just shows it gave for 100 PeV air shower, what that signal looks like in photons density in terms of on orbit at 525 kilometers. And you can see you have a width of 100 kilometers and a really strong signal of the order of nearly 80 gammas per square meter. We have a collection of, actually when we're tilted, about 2.5 square meters, so you could figure out the statistics there. This is for an Earth emergence angle of 10 degrees, assuming the air shower started at sea level. So for transient, we have to understand what we're doing. So that a transient goes off, we tilt and then look, and the actual sensitivity is defined where the source is located in the sky, and if you will, and how it kind of dips go below in a certain band below the Earth. So, we can see maybe say 20 degrees of Earth emergence angle that translates into a different angle from away from the limb of the Earth. But these different curves just show how sources go in terms of their viewing and their position in the sky. And in this case, we're actually doing it for the SBB2 experiment. We've been recently adapting all the analysis and tools did use for Poema for SBB2 for when it flies to really prove the physics with actual data from the flight. So the fact is, the takeaway of this is that depending upon where the source is, your sensitivity is going to be different. And that kind of translates into it here for Poema. So this middle plot kind of gives you the sensitivity in terms for one orbit. So when the source kind of hangs out near the horizon, you have really good sensitivity. And then you have a lower one over the average. And that defines, if you will, our sensitivity bands. These are 90% confidence level bands. That you could see that what you have is for the majority of it, you're in this dark band here. But there are cases if the source is, Goldilocks, is in the right place, you end up getting the source here. And this shows our sensitivity as a function of energy for short bursts and then for also binary neutron star mergers. And I want to point out too that we actually chose these in the paper because these tend to have harder spectrum that may be not seen at lower energy experiments like IceCube. The band for IceCube is shown here is because for GW 17087, it really wasn't in an optimal position for IceCube. So we did an analysis to make sure we covered all the potential space to do a fair comparison. So as you can see, we have very good sensitivity above the energy scale, about 20 PeV. And like I said, we could tilt. The nature of the experiment is such that we could follow sources once we get an alert. So how this compares, I kind of showed this first plot before, so this is kind of in a different way. So the two left plots are Poema, the middle plot are for IceCube, and the right plot is for a specific configuration of Grand, assuming all the experiment is at one location in China. But what you could see is that inherently, because of the nature of it, you do have blind spots when you're on the ground, but when you're in orbit and able to tilt, while you don't have uniform coverage, you do cover the full spy. Again, the benefit of going to space to do this type of measurement. On just what our potential is for detection of these things is shown here. And so depending upon, we went through and did analysis. This is done by Tony Venters, and it's in the PhysRevD publication, going through all the various sources, that we looked and see what the optimal ones were and looked at the Poisson probability of, based upon these models, seeing what is the potential that, say, in a 5 or 10 or even 15-year mission, what is the potential of observing one of these with the current knowledge of the sources. And so while you could say you can go out to a certain distance, that tells you your capability of it, but how often do these things go boom? That's this plot, right? That tells you what the frequency and the chance of seeing things are. So just to give a summary, so really Poema is designed to really answer the question of ultra-high energy cosmic rays. What is the source of ultra-high energy cosmic rays? We have all sky coverage to increase exposure. The stereo fluorescence technique is key with the good angular resolution to be able to do the composition, anisotropy measurements, and also achieve good energy resolution. For free, when we're doing this, it comes to really exquisite ultra energy neutrino sensitivity to all three flavors. And we have the capability of tilting to the Earth when we get a alert to look to see and to reduce our energy threshold for neutrinos to 20 PeV. And really this highlights too is the nature of using the optical Cherenkov, say, versus the radio. Even though this is done in moonless nights, we are assuming about a 20% duty cycle for the neutrino measurements, about 13% for the fluorescence measurement. You have to take that hit. We have to work at dark moonless nights. But even so, you're able to achieve with an instrument with 2.5 square meter collecting area, 20% average PDE. You're talking of going down to 20 PeV from low Earth orbit. And you can argue that there may be possibilities even extended down further. Other things which I cannot talk about, I don't have time to talk about. There's a nice paper by Claire Leupin on the sensitivity for decays of super heavy dark matter into neutrinos in both the 20 PeV and above, and then the 20 EeV range, which are really, really interesting. The limits are really good. And so where we are, so we're waiting the results of the Astro 2020 recommendation for the NASA probe. So the way we're taking this at Goddard is that we're assuming that this is going to be a green light. We're going to assume that we're moving forward and thinking that NASA will try to make a recommendation to put out a probe AO in the near term. And so we're trying to gear up ready for that. We're also building upon the neutrino studies because, like I said, it was quite interesting in regard to the capability we saw with a modest size, say 2.5 square meter collecting area, in terms of the neutrino performance, and seeing potentially if there's other platforms, including maybe something on the space station or even a small sat type platform that could potentially do this. So the plots up on top, again, I just forgot to mention, but I'll reinforce the capability for UHE And so what that's shown there is the limits, the lines are basically the limits limiting spectral recovery. If one is there, we'd naturally go and try to optimize for more exposure by tilting. And then also too, I want to show the right plot for the new T response. This is we call it the duty cycle weighted. So you look at this band here is for Poema. This is another band if we could increase it to, excuse me. This band here is for diffuse down here. This one's more corresponding to the band for target of opportunity. And we degraded this by a factor of 5 because we put in we have a 20% duty cycle compared to IceCube. We assumed 100% for their high energy starting events just to show where the comparison is. If you're lucky and the source goes off boom, you actually have really, if it happens in time while you're viewing it, this actually curve should be 5 times higher. And so this kind of leads into, we have a NASA funded program we call New Space Sim, which is really carrying out the development of the simulation we did for the neutrinos to do an end-to-end and including the radio part of the simulation, and that we're doing it naturally for ourselves, but also for the community. And we have a couple of ICRC papers I suggest looking at that. And really what we're waiting for finally is just on the SBB2 flight coming up. And this basically shows the wealth of phenomenon that we're going to be able to explore with this flight. And including one that I didn't show is that the ability to see cosmic rays interacting over the limb, so basically not coming out of the Earth, but over the Earth in the Cherenkov with a threshold down in the tens of PeV range, with the count rates of the orders of 10 per hour. So there's kind of a guaranteed signal, if you will, to test the components of the Cherenkov telescope with the SIPMs to understand what the Cherenkov signal looks like. Naturally, we'll also do a search for diffuse and even target of opportunity. It turns out that the target of opportunity analysis, we do have sensitivity to things going boom in nearby galaxies, like say Andromeda. Now, whether they happen, who knows, but at least we have sensitivity to that. There's a nice paper by, I think Tony Venters has it in the ICRC coming up. And then also too, that we call these anatons, there's some sensitivity. If you recall, the ANITA experiment had these anomalous events that slant depth through the Earth really didn't indicate it could be a tau neutrino because of the depth in the Earth. And so there was much speculation, and even I remember an article about was it backwards energy waves from parallel universes causing these. Was an article, but in any event. But we have the sensitivity to basically see this in fluorescence if something is there. Recall with the radio with the NITA, their energy threshold is about 10 to the 18th. Our energy threshold is in SBP2 is more closer to 10 PeV, so 10 to the 16th. So if there's something there with a natural spectrum, I think potentially we'll see that. And so I will end that here, and then I will entertain questions, and thank you very much.
Thank you very, very much for this nice and complete review of this project. Unfortunately, we are almost run out of time, but we have time for a quick question if we have. Pier Simone, please.
I know
Yes,
Pierre would ask me a question.
Hi, Francis. I have a couple of questions that reflect my ignorance of this field. First of all, this experimenter is free running or has a trigger? And then the second question is, you say you get a very nice energy resolution and composition, X max, sigma less than 30 grams per centimeter, and blah, blah, blah. But my question is, how do you calibrate this object?
Okay, so the first question is that each instrument is going to be triggered, collect data it's on its own, and then it goes to the ground for analysis. So there's no inner satellite, if you will, triggers, right? You have to do the reconstruction on the ground. For calibration, there's going to be things called, they're actually doing that now with laser shots with mini USO. You could do laser shots on the ground and basically do a calibration type beam up in the atmosphere. The other thing is that we, in regard to the atmospheric conditions in this neutrino simulation program, we're actually pulling from Earth Sciences as a wonderful database of all the measurements for clouds, for aerosols, for ozone, called MERA2 that we're pulling out of and looking actually doing a data-driven approach for the study. So given with lifetime measurements, with calibration, whatever, we feel that we, you know, well, the devil's going to be in the details of seeing it, but at least we have a path that we think we can understand the energy scale of the instrument.
Okay, thank you.
There's also on board, which I didn't say, like pulsars or whatever, LEDs to test the optics and calibrate the focal plane and everything else. Right, so there's inherent stuff that's happening there, and through the spectrum of the trunk-off. You know, the hard part is that, you know, I didn't get to talk about it, but the air, you know, the really dominant background is due to dark sky air glow. Everyone's used to working in the fluorescence where it's about 500 photons per square meter per nanosecond per steradian. When you look in the band going from 300 to 1,000, it's more like, you know, 15,000. It just, that's the nature of it. And that's, but that helps with the nature of the trunk-off timing being shorter, 10, 20 nanoseconds versus a microsecond really helps with that. That's what we use to determine the thresholds, if you will, for these instruments. So those thresholds were used for the instrument were science thresholds we set to guarantee that, say, a false neutrino, or someone once called them fake news, would have and that's a graduate. It was actually a postdoc from University of Chicago at a conference. I'll give him credit for that. But that happens at the less than, like, say, less than 1% per year, right? So we set the threshold such that we have, you know, when we do these studies, we have very low background in terms of a. Naturally, you set the threshold higher because you could tolerate a little bit more bandpass. You understand the background, but at least for the science analysis, you want that threshold high enough such that you don't have any background in your signals. So,
okay, thank you very much.
I hope I answered here.
Thank you again, and I would like to thank at the end of the session all the speakers that kindly joined us today with very nice and interesting talk. I hope it's been interesting for all of us. And I will left last word to Ivan, if he managed to connect. Probably is not.
I have seen that Ivan is also in Poema, so he's ubiquitous, right?
Hand in everything, or a foot in everything.
Okay, probably Ivan is not listening. So I would like again all of you for joining, and I invite you to follow other session of this 16th edition of Marcel Grossman. Thank you, everybody, again, and see you.
Bye, everyone.
Bye.
Bye-bye, thank you.
Thank you again.
Bye.
Again.